Okay, at least you should imagine that's a blackboard. It's the...
Okay, we're in live now.
Fantastic. Okay, so okay, should we start?
Yep.
Yeah, cool. Okay, so welcome everyone to our seminar, El Seminario Tartaglia. I would like to introduce today's speaker, Dominik Kwietniak, from Jagiellonian University in Krakow, in Poland. So just let me say a few words about Dominik. Dominik did obtain his PhD at the Jagiellonian University and also his Masters of Science in Mathematics, all of them with honors, of course. And well, Dominik is one of the world's specialists in dynamical systems, in particular in ergodic theory, symbolic dynamics, and topological dynamics. And today he will speak about on intrinsic ergodicity of B-free shifts and their relatives. So welcome, Dominik, and please start when you want.
Okay, thank you very much. Thank you very much for your patience. Sorry for a little technical difficulties at the beginning of my talk, but I will not go into overtime. I hope we will still finish on time. So it is my great pleasure to be. I think this is my third. Okay,
it's correct. The third time, yeah.
In San Luis, maybe the first not live, just online. And at least my second talk at the El Tartaglia seminar. So, okay, guys. So I will. So what I'm going to do is I'm going to talk about joint work we have with Michał Kupsa, Jakub Konieczny, and recently Melih Emin Can, PhD student in Krakow, but he's originally from Turkey, joined the team, and myself. So those are the authors of this talk, and so what I'm going to tell you also is a kind of a new or maybe refreshed approach to results by some other people. And for a better clarity of presentation of mathematics, I will not dig into the details who proved what and when. I'm sorry. I'm sorry for that. If you look into papers or preprints, all informations are there. Okay, so I prefer to tell you a story without too much historical digressions. So this is what is happening here. So okay, let me start with a definition. So a natural number is square free if for no prime p squared divides n. So for every p prime, actually p squared does not divide n. So we have a nice set of natural numbers, so of square free numbers, and well, which numbers are square free? Okay, let me start with 0. Okay, and of course, what will happen is that, well, 0 is not square free, and 1, 2, and 3, they are square free numbers. 4 is not square free because it is divisible by 2 square. 8 is not square free. 9 is not square free. 12 is not square free. and later 16 is not square free. The remaining numbers are square free. Okay, so this is the first definition. Okay, what can you say about the set? Well, plenty of things actually, but the question is, what can you say about this set using dynamics? So to use dynamics to tell something about the set, you introduce a usual trick, which I don't know, maybe is the first one to do this trick. It seems that it was Furstenberg. So what you do, you write like F for the square free numbers, and then you introduce the characteristic function of F which you pretend to be an element of a set of all sequences, of all binary sequences indexed by non-negative integers. So in this case, our characteristic function will look like this: 0, 1, 1, 1, 0, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 0, etc. All right, so this is how we turn the square free. Yeah. So we have this characteristic function, and we pretend it to be. So we pretend this set is sometimes denoted as omega 2, the full binary shift. So all binary valued sequences over the non-negative integers. And of course, we may consider dynamics over the set by considering the shift operator sigma. So we have now the problem of studying a single sequence or set of numbers becomes a problem of studying a special point. So the characteristic function of square free, I don't know, x with the subscript f, becomes an element of my full shift space, and I may study it there. But of course, okay, why analysis is useful? Analysis, or this kind of approach to things, is useful when you can do some pass to the limit. So well, maybe this is too philosophical sentence and too vague to be like a deep one, but in some sense, our gain from using analysis comes from the ability to pass to the sequence, to the limit. So single sequence in the full shift is maybe not interesting. So instead of taking the single sequence, we consider the orbit of my single sequence with respect to the shift operator, and we take the orbit closure. And so this is the closure of the set sigma to the power k of x, small x with subindex f, when k runs over non-negative integers. So we take, now we use our dynamics and we turn our we turn our problem from a single sequence. We create an orbit, and from an orbit we take the orbit closure, and in this way we obtain a subshift. So this subshift is called square free shift, and in a more general way, you can imagine that you started with a shift, which is defined how it is defined. You start with a set. So in case of the B square free shift, you started with a set which is a set of squares of primes, and you took a subset of those integers that no elements of the set B divides our integer. So B free integer n is B free integer means that for every B does not B does not divide n. So you can generalize the set of square free numbers by taking a set of B free numbers when B is any set of integers. So for the square free integers, the example of the set B is squares of primes. So, well, by the way, of course, feel free to interrupt me at any time and ask questions if something is not clear. So, okay. So this and again, taking the characteristic function of B free numbers for some set B, we can consider its orbit with respect to the shift, and we obtain a B free subshift by taking the orbit closure of this characteristic sequence. So this is all there. This is somehow many people studied those subshifts, and let me propose an approach to studying those subshifts based on the following observation. And again, I will start with square free numbers as my guiding example. So what is happening here is that okay, I went a little bit too far with the okay, and my program for writing collapsed, and I have to restart it. Sorry. Sorry. Okay. Okay. And all my nodes so far are gone. But okay. I hope that you remember something from what I said so far, and I will still start to share the screen. Okay. Okay, so well, all the nodes so far are gone.
So you were at the point where you define a set by forbidden to be divisible by another set.
Yeah.
And that's it. Yeah.
So let me make the following observation. If B is finite, so B, for example, is really B1 up to Bk, then if I agree that I have n0, so those my non-negative integers, then B free integers are just obtained if I remove from my set of integers all multiplies by of b1 up to bk. So this is b3 integers in this special case. And now observe the following, that b finite implies that the characteristic function of those b3 integers under this assumption that b is finite is just the periodic sequence. Okay, and of course, then the b3 shift is a periodic orbit. So now remember, I wrote for you a characteristic sequence for b3 integers, which starts like this: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 21, etc. Right? So this is the characteristic sequence. And look, my first square of integers, so is just 4. So the sequence or singleton of 4 free integers is simply a periodic sequence. 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0. Maybe well, my columns are, yeah, it's okay. So 1, 1, 1, 0 again, 1, 1, 1, 0. So this is my sequence right now, and here we have the periodic sequence. So observe the following. Of course, the set of all square free integers is a subset of the set of singleton of 4 free integers. Moreover, now if I introduce the following construction of taking a hereditary closure of a shift space, so it is something which is a well-known trick. But let me save. Okay, for a moment, simply save this. Okay. Just in case. So now what is happening here? I'm sorry, I have a terrible some terrible problems with my tablet. It doesn't want to collaborate with me. But anyway, let me try to write still on what I have here. It is like now I can, if x subset 0, 1 to infinity is a shift space, then I define the hereditary closure x tilde of x as a set of all x binary sequences such that there exists a sequence y in 0, 1 in x, I'm sorry, in x with the property that x is dominated by y coordinate wise. So this is a coordinate wise comparison of two infinite binary sequences. So for example, in our example, we see that maybe in the final characteristic sequence of square-free integers, which is my white sequence written below, some of the ones from my periodic sequence written in red are replaced by zeros. So this means that maybe this means that the characteristic sequence of the B-free integers is not a member of the periodic orbit obtained by considering a singleton of 4 free integers, but the characteristic function of the square-free integers is still a member of a hereditary closure of this periodic orbit. And one can see that, in fact, the hereditary closure of this single, okay, it seems that they are, well, now as you can see, something strange happened because I recovered everything. So the previous nodes are also there, maybe not in the right order. So what is now interesting is that we can simply notice that if I have a periodic orbit like this periodic orbit written in red above, then this periodic orbit can be represented by a labeled graph when I have 3 ones followed by 0, and then starting at any vertex of this graph and following the edges of this graph, I will obtain all possible periodic sequences in my periodic shift written above. But now, taking the hereditary closure tells me that I should be able to consider each time I see 1 in my periodic sequence, I can replace it by 0. So a graph describing the hereditary closure of, so this graph describes the hereditary closure of the singleton of 4 free shift, which is, as we know from the above, simply a periodic sequence. So, and what is more is that the characteristic function of B-free, square-free integers belong to this hereditary closure. So chi f belongs to this to this shift. So what will be the next step? The next step would be to consider the shift which is obtained by taking 4 and 9 free integers. Right, so those are the first 2 squares of primes, and this is of course a sequence which goes 1 1 1 0 1 1 1 0 0 1 1 0 1 1 1 0, and I should be careful. This is now 16 17 18. Okay. This is a characteristic function. So this time I won't be able to write you a graph. Okay, I could write you a graph, but this is a periodic sequence with a primary period of 36, 4 times 9. So it will be a quite tedious thing to do, but I will observe the same mechanism. And the same mechanism tells me that taking the first 2 integers, taking this in my set B, and taking the set B1, B2 for those first few integers, 3 numbers, this will be the characteristic function of the set will be a periodic sequence, So the orbit closure of the sequence will be a periodic orbit, and the hereditary closure of that periodic orbit, it will be a shift space, which can be described by a graph like here. So those shifts are known to be suffix shifts. So this hereditary closure of the periodic orbit will be a suffix shift containing my final B free shift. So continuing in this way, we obtain a sequence of suffix shifts which have this property that they are getting smaller and smaller. And in the end, we have our, what letter I used for? Okay, so here I use XF. So square free integers are here. By the way, it can be proven using the Chinese reminder theorem that actually square free shift is hereditary by itself, so it is equal to its hereditary closure. So we have a nice approximation. Well, we don't know if we have an approximation, in fact, but we may want to study what is going on there. So what is the situation we observe? It is that possibly we have a situation when a sequence of simple shifts approach, in some sense, a shift which is possibly more complicated. And we want to answer the following question: can some properties of this final shift be deduced from the properties we can more easily see in the approximatic sequence? So let me remind you that every shift space, in fact, has a naturally defined sequence of so-called Markov approximations. So I hope that you more or less are familiar with some nomenclature of the shift spaces. So shift spaces are always defined by defining a set of forbidden words. And then we, having a set of forbidden words, we form a shift space which consists of all sequences in the shift space such that no forbidden word appears somewhere in my sequence as a finite subword. So, of course, so every shift space is defined using a family of forbidden words. Some shifts to be defined, they require infinite families of forbidden words. So observe that a shift here, which is the set of all possible labels we can read from starting a walk on this graph at the random vertex. So this set has the following property, that for some residual class of rests modulo 4, every coordinate has to be 0. So in other words, all the sequences in this hereditary shift described by my graph, they have to have this property that either they are a form of 0, 3 free places when I put anything, and then 0, and then again 3 free places when I can put everything and then 0, and then 3 places when I can put everything 0. And this is the first possible pattern I can see. And I can see 4 more patterns when zeros have to appear like on every position here, etc. Or 0 have to appear at every position here, etc. So in other words, I have to see 0 along some, so a point is in my shift, even only if for some arithmetic sequence with difference 0, with difference 4, I see zeros. And then the remaining positions I can fill in however I wish. So of course, this shift cannot be described by the finite set of forbidden words, because in some sense, the forbidden words are all words when not every fourth element along some subsequence is not 0. I have to keep this in my memory all the time, and then I have to put an infinite set of forbidden words to describe this shift, and it can be proven that no finite set will be good for this shift. So this shift will be like a proper shift which requires infinitely many words to be described, as infinitely many forbidden words to be described. So now what is happening is that there are, of course, shifts for which only finite set of forbidden words is sufficient to describe them, and those are called shifts of finite type. And then every shift you can imagine, it is given by the set of forbidden words. So you may again just take supershift of the subshift by forbidding like the first forbidden word from your list, then the first 2 forbidden words from your list, and then the first 3 forbidden words from your list of forbidden words. So eventually you will get shifts which are defined by the sets of forbidden words, which are all the time finite, but more and more similar to the set of forbidden words of your final shift. So this is in this way you obtain very nice sequence of so-called Markov approximations to your final shift. And then what is happening that those Markov approximations, they do converge to your final shift in the Hausdorff metric topology. So what does it mean? It means that whenever you take any alphabet and you consider a full shift over that alphabet, then, so this is a compact metric space, and subshifts are compact subsets of that compact metric space. And therefore, a natural topology for the space of subshifts, so what will be the space of all subshifts? This will be all sets X contained in the full shift, such that X is closed, X is non-empty, and say sigma X is contained in X. So this will be a set of subshifts, and this is so this is subshifts are special compact subsets of your full shift, and therefore you may consider, because the full shift is a compact metric space, you may consider Hausdorff metric on the space of all compact subsets of your compact space, and you can consider the space of all subshifts as a special subspace of your hyperspace of your full shift. So the space of all compact subsets and those with the Hausdorff metric are usually called hyperspaces. So in you have a hyperspace, and the space of all subshifts is a special kind of a hyperspace. And these Markov approximations I mentioned, they approximate exactly your final shift in the topology given by this Hausdorff metric on your space. So let me quickly maybe remind that if I have X row a metric space, and if K and L subset X are non-empty and compact, then the Hausdorff metric associated by corresponding to the metric row on the space between your non-empty compact subsets is defined in the following way. So this can be defined as the infimum over all epsilon greater than 0, such that K is a subset of the epsilon hull around L, and L is a subset of an epsilon hull around K. So what is the epsilon hull? If I have a compact subset K here, then all points which are at most epsilon close to K, they form this epsilon hull. So two subsets. So if I have two subsets, white K and red L, and then I build those epsilon hulls around them. So if we have a picture like here, then we know that the Hausdorff distance is smaller or equal than epsilon. So the metric you have for this kind of approximation is the Hausdorff metric coming from the usual metric on your shift space. Well, but of course, this approximation is not good. So I think that Gallo with Hazotes, René Hazotes, and some other guys, you have your beautiful paper on that because every shift space has an approximation, then not much can be said in general. But if the speed of approximation is somehow controlled, then you can say something more. There's a very nice paper about that. And this is one of the possibilities. And the other possibility is what we propose is to change the metric, or maybe introduce a pseudo metric. So for the shift space, if I have X in A, X and Y, the shift spaces, then I can introduce the D bar pseudo distance between those two sequences in the following way. I take a limit superior as n goes to infinity, 1 over n from the number of coordinates such that my two sequences differ. And this is only a pseudometric because it is sometimes 0 for two different sequences. But it is always bounded because this distance is always at most 1. And therefore, I can introduce a D bar Hausdorffification of this metric between the shift spaces. So this is, of course, defined in the same way as the Hausdorff metric above, but this time I put D bar in place of rho, and I repeat my definition. And even the space is no longer compact, I can still see that this will be a pseudometric for subshifts. And now I can see in this language, I can now phrase the thing, which is the crucial observation here, that if we have those square free integers and we have this approximation of a sequence of square free integers by the sequence of suffix shifts obtained by taking hereditary closure of periodic orbits, like here, so then this, in fact, turns out to be an approximation with respect to this Hausdorff metric version of D bar. So this is, of course, well, a consequence of properties of square free numbers. So this was known for a long time, but the language in which the result is stated is new. So this Hausdorff distance goes to 0 as k goes to infinity. So our guiding example here is that you may see the situation in which a sequence of shift spaces approximates another shift space in a special way. And there's a moreover part, and this moreover part tells us the following, that, this d-bar pseudo-distance between sequences corresponds roughly to the d-bar to the d-bar distance between measures. And the d-bar distance between measures has been used to study, for example, Bernoulli measures. And every shift invariant measure on the full shift has also a sequence of so-called Markov approximations, so that for every shift invariant measure on the full shift, there exists a sequence of Markov measures approaching to my shift invariant measure in the usual weak star topology on the space of measures. And it turns out that there's a characterization of Bernoulli measures through the following fact, that a totally ergodic measure is Bernoulli, even only if it is a d-bar for measures limit of its own Hausdorff approximations. And one of the theorems
Markov approximations.
Markov for measures, yes.
Yeah.
So one may now ask for the following question. So total ergodicity corresponds to the fact that the Markov approximations, so shifts of finite type approximations, should be mixing. Can we say something about space, the space of subshifts, which can be approximated using shifts of mixing shifts of finite type with respect to this d-bar Hausdorff pseudometric? And it turns yes, we actually can. So we have the following theorem, which says that if if X is chain mixing, so chain mixing means that the shifts, this is actually equivalent to the statement that the shifts of finite type approximating your space are all mixing. So if X is chain mixing, then this and Xn denotes SFT approximation of X up to the forbidden words of length n. Then we have that this goes to 0 even only if X has the following property, that this is, well, we need to assume that that's a surjective. And the second thing is that for every epsilon greater than 0, there exists a natural number capital N, such that if W1, W2 are words in the language of X of length greater or equal than N, not necessarily the same length, then there exists a point Y in X such that the d-bar distance between Y and this concatenation, W1, W2, etc., is smaller than epsilon. So this property we called d-bar shadowing. And this property tells you the following nice thing, that if you try to define a topological version of a Bernoulli measures using the same mechanism as this characterization of Bernoulli measures, then you obtain a class of subshifts which can be characterized intrinsically by this property. And it turns out from this theorem that basically all possible generalizations of the specification property leads to the shifts which are in this special class of subshifts. And you can now ask yourself what kind of properties are translated by this special D-bar approximation of subshifts. Well, for example, entropy density. Entropy density for a subshift means that for every epsilon greater than 0, and for every mu a shift invariant measure, there exists nu an ergodic shift invariant measure on your subshift, such that the measures mu and nu are close, and the entropies of those measures are also closed. So every measure can be approximated in the weak star topology, and entropy arbitral well by ergodic measures. And now it turns out that if I have this approximation in the sense of this D-bar Hausdorff metric, and if I know that every sequence here, every xn here has entropy dense set of ergodic measures, then my limit in the sense of D-bar Hausdorff metric also has this entropy density. So turning back to my B3 numbers, it can be easily seen that each of the suffix shifts has entropy dense set of ergodic measures, and therefore my square free shift has an entropy dense set of ergodic measures, which may not be that easy to see at using the definition. But for those square free shifts, it is now relatively, this is an easy consequence of this general theorem we have. And actually, I will not have to tell you more about it. You can also use it to somehow analyze the measures of maximal entropy for those B3 shifts. Using the picture we have here, one can show that those suffix shifts described by graphs, they have unique measures of maximal entropy. And by observing that those unique measures of a maximal entropy, then they have to approximate the measure of maximal entropy for the square free shift. You may prove uniqueness actually, but I will not have much time to tell you about it. But then with the very same methods, you can also consider other families of subshifts, which are constructed in the similar way. So you can actually start with any sequence of suffix subshifts, which are descending. So you are getting smaller and smaller subshifts. And in the limit, if you are careful, the limit will be D-bar approximable, and it will inherit all the properties from your approximating sequence. Okay, so I think my time is up, and I'm sorry for taking longer than expected. I had some technical difficulties today. I don't know, maybe simply my tablet was uploading some update of some programs or something, but it went smaller than usual. Thank you very much for your attention.
Thank you. Well, let's give our guest a virtual applause. I think there are some emojis after that. I don't know if there's anyone with a question.
Yeah, I have some questions. Okay. So the thing is how to check, how to verify that that you have this property in a practical case. For instance, in the case of the square free. What is the secret? How can you guarantee this? The fact that you are converging in the bar.
Mm-hmm.
That yeah.
So for square free and in general B free, there's a theorem of Erdős and Davenport.
Mm-hmm.
And it tells you basically that each characteristic sequence of a B free can be approximated, that the sequence of this periodic approximations has at least this property, that the lower bar, an analog of this xn when this is n periodic approximation, and then characteristic function at the end, this goes to 0.
Okay.
And for nice cases like a square free, you can replace it by this. And then I mean, it is net you in the case of some numerical sequences, you hardly ever have it for free, but it happens. Well, you may people were considering a D-bar closure in the full shift of all periodic sequences, and as far as I know, to tell whether you are in this of periodic points in A infinity. So I don't know if there's an intrinsic characterization where you are there, but for sure there are many sequences which have been shown to be there.
Okay.
If
you take an hereditary subshift for one of those sequences, then it's okay.
Yeah, then it is immediately okay. You can also play with so you know, you pick your favorite number between 0 and 1. Take its decimal expansion. Of course, assume that this is not rational, because those are more interesting ones. And then take its decimal expansion, and then look at the rational approximates of that from the above. And then you see that this function, that this expansion is a point in the shift over the alphabet 0, 1 up to 9, but those approximations from the above will also converge in the D bar. Way they have a chance to and so if you now build a subshift around that,
in particular you have so in particular you solve in this way the problem for the beta shift, for instance.
Yeah. So all beta shifts are in this class of even this D-bar shadowing class.
Uh-huh.
They have even better properties. So we know that they are minimal examples in that class. So what we know? We know that any shadowing property, the usual shadowing or some more weaker versions of shadowing existing in the literature, they all lead to this D-bar shadowing property. So they all guarantee that you are approximated in this way. And we also know that if you work a little bit artificially, but if you work with those software approximations in the clever way, you will get minimal subshifts, which are maybe interesting because they are minimal subshifts, but still simplices of invariant measures, they look more like simplices of invariant measures of mixing shifts of finite type.
Yeah, but with this technology, you are always in the chaotic part of the spectrum. So yeah.
Yeah. I have to be because okay. I may also consider D-bar limits of some simpler classes, but I don't know where it will lead. This is something which I don't know. It is the same like with the space of measures, right? The space of measures, you know that the measure is Bernoulli, even only if it is a D-bar closure of its own Markov approximation.
Yeah. Okay, but thank you for me. So it's everything. Thank you very much. This is a very powerful approach. I appreciate it very much.
Yes, thanks for the talk, Dominik. So, and what about so for bounded density shifts? Do you have this D-bar shadowing? I don't think so, right?
Not always. I don't think that this is always the case. I think that that of course you have some when you have it, right? But we are not, yeah. So yeah.
Okay. But
here's a question which for the bounded density shifts, you also have this characteristic sequence, kind of this maximal density of one sequence. And you know that because this is subadditive, then the single symbols, there's a density, right? If it is binary, then there's a density.
Yep.
But do you know actually how about other blocks? If I take this characteristic sequence and I take a blocks of length n2, does every block of length 2 has a density? I think the answer is no, but and this also shows that this cannot, because if you are, say, a D-bar limit of periodic sequences, then you are actually a generic point. So every block appearing inside you will have a density of occurrences. So yeah.
I see.
Do you have any other questions to the speaker? Well, if there are no more questions, then I would like to thank Dominik again for giving a talk.
Thank you, guys.
And we'll meet next week. Well, Dominik already knows the Physics Institute in San Luis, but we now have a new one.
Yeah, so new one I don't know. I've been there in the old one still.
So you have to come again, so you can.
Yeah,
Yeah.
one day, yes, one day.
You will know yeah.
Okay.
I hope it will be possible. So thank you very much. It was a pleasure to give a talk, even if only online.
Yeah, thanks a lot, Dominik.
Thanks.
Have a good night.
Yeah, thank you.
Good night.
Same to you. Have a good day. Yeah.
Yeah, we're just having breakfast.
Yeah, okay. Okay.
So see you.
See you. Bye.
See you. Bye. Okay. Bueno. Bye.
Bueno, y nada más, antes de que se vayan todos, la próxima semana tenemos a Víctor. Va a ser presencial en el instituto. Bueno, entonces nos vemos. Hasta luego.